Following the discussion of the previous video on photogeneration, we will now go further in describing what happens to a semiconductor material under illumination. In particular, we will look at what happens to the Fermi level. Let's start by looking at an intrinsic semiconductor. Here you see an intrinsic crystalline silicon at thermoequilibrium using bonding model representation. At a temperature above 0 Kelvin, mobile electrons and holes are present in the material. You should remember that the concentration of electrons and holes is equal to the intrinsic concentration Ni. In crystalline silicon, at room temperature, the intrinsic concentration is 1 times 10 to the power of 10 per cubic centimeter. The absorption of photons with energy higher than the band gap leads to the generation of extra electron-hole pairs. This brings the system into a non-equilibrium state. In this video, we assume that the illumination will increase the concentration of electrons and holes by 1 times 10 to the power of 15 pairs per cubic centimeter. We call the increase in concentration the excess carrier concentration. In case of illumination, the concentration of excess electrons, delta N, is equal to the concentration of excess holes, delta P. Here we have our familiar band diagram of an intrinsic semiconductor. You can remember that the Fermi level is located close to the middle of the band gap, between the conduction and the valence band edges. The Fermi level energy represents average energy of the valence electrons in the material. The carrier densities are equal to Ni. And the mass action law applies, which means that the product of N and P is equal to Ni squared. The average energy level of the electrons and the average energy levels of the holes both sit at EF. Now let's illuminate the material and see what happens. Remember that we are adding extra 10 to the power of 15 charge carriers in addition to 10 to the power of 10 carriers present in crystalline silicon at the thermal equilibrium. This is an enormous change in the concentration of charge carriers. We have now much more electrons occupying states in the conduction band and much more holes occupying states in the valence band. But how does this affect the Fermi level? First, let's draw the Fermi level of the intrinsic semiconductor at thermoequilibrium, EFI. The Fermi level is used to determine the concentration of both electrons and holes at thermoequilibrium. When illuminated, many more electrons and holes are present in the material. By moving the Fermi level closer to one of the band edges, we will help to determine correctly only one type of the carriers, not both of them. In order to accurately determine the concentration of electrons and holes in non-equilibrium state, we need two energy levels, one for electrons and one for holes. We call these two energy levels quasi-Fermi levels. EFN represents the quasi-Fermi level of electrons, and EFP represents the quasi-Fermi level of holes. So, going from equilibrium state to a non-equilibrium state, instead of using one Fermi level for describing the concentration of electrons and holes in semiconductor, we use two quasi-Fermi levels. A consequence of this situation is that the mass action law does not hold, and the product of concentration of electrons and holes is not anymore equal to Ni squared. Let's determine the carrier's concentration in illuminated semiconductors. For a system in equilibrium, we determine the carriers densities occupying the states in the conduction and valence bands. As you can recall, they were function of the position of the Fermi level with respect to the edges of the conduction and to the valence bands. The same can be done in a situation of non-equilibrium. The difference is that now we have to consider two quasi-Fermi energy levels. For the density of electrons excited to the states in the conduction band, you have to use the difference between the conduction band edge and the quasi-Fermi level for electrons. For the concentration of holes occupying the states in the valence band, you need to use the difference between the valence band edge and the quasi-Fermi level for holes. You can use these equations to calculate the quasi-Fermi level positions for a given charge carrier density in a non-equilibrium situation. I invite you to solve these equations for our example of silicon at room temperature with an injection level of 10 to the power of 15 charge carriers per cubic centimeter. It is also important to mention that in non-equilibrium state, the law of mass action is no longer valid. The product of carrier concentration is no longer equal to an I square. In addition, the product N times P cannot be determined only as function of the band gap energy. Instead, we also have to take into account the difference between the quasi-Fermi level energy levels. This results in the presence of this exponential term. We have looked at an intrinsic semiconductor under illumination. Let's change to doped semiconductors. Here you see carrier concentration for N and P-type silicon as we calculated in a previous video. I will not go through these calculations again, but we can use these results to determine the quasi-Fermi levels under the same illumination conditions as in the case of intrinsic semiconductor. Let's start with N-type silicon. We use a donor concentration of 10 to the power of 18 per cubic centimeter. You can recall that in equilibrium, the electron concentration is 10 to the power of 18 per cubic centimeter, and the hole concentration is 10 to the power of 2 per cubic centimeter. This results in a Fermi level position of 0.09 electron volts below the conduction band edge. So what will happen when we illuminate this semiconductor? Let's assume that this illumination adds 10 to the power of 15 charge carriers per cubic centimeter. Well, you may notice that this injection level is far below the equilibrium concentration of electrons of 10 to the power of 18 per cubic centimeter, but far larger than the hole concentration of 10 to the power of 2 per cubic centimeter. This means that the electron concentration will be almost unaffected and remains at 10 to the power of 18 electrons per cubic centimeter, while the hole concentration will simply be equal to our injection level delta P. So what does this do to our band diagram and position of the quasi-Fermi levels? Well, since our electron concentration does not change significantly, the quasi-Fermi level of electrons stays at the same position as the Fermi level in the N-type semiconductor at equilibrium. However, the position of quasi-Fermi level of holes has to be added in the band diagram. This position can be calculated by using the equation I presented a couple of slides ago. The position of the quasi-Fermi level of holes is 0.25 electron volts above the valence band edge. What is important to take away from this example? The message is that when we have moderate to high doping and this level of illumination, the position of quasi-Fermi levels of the majority carriers does not change with respect to the position of the Fermi level at equilibrium. In addition, we have to introduce the quasi-Fermi level of the minority carriers into the band diagram. The same thing will happen for p-type semiconductor materials. I invite you to try and calculate the quasi-Fermi level positions. In this video, you have learned about quasi-Fermi levels when non-equilibrium conditions occur in a semiconductor. In the next video, we will discuss how charge carriers move through a semiconductor, introducing different transport mechanisms.